Okay, so minimum velocity. We're going to start out by talking about minimum velocity, and then we'll talk about maximum velocity. And our discussion is going to focus on the same point, which is the highest point in a circular loop. So look at this situation here. We have this roller coaster car going through this loop, which is assumed to be perfectly circular. So like up here at the top is like the top portion of this loop. Even though as a whole it looks like an oval, the top portion of the loop right here is assumed to be perfectly circular. And you would have to be given the radius of the loop. The radius of the loop would have to be given. All right. Assuming that this car is not attached to the track, which you don't have to worry. When you go to an amusement park, the car you're riding in will be attached to the track. But let's just pretend that you're at some real ghetto amusement park. You're at some ghetto park and this car that you're riding in is not attached to the track. So if you go too slow through the loop, what's going to happen? You're going to fall off. You're not going to make it through. So there's a minimum velocity that an object must have to make it through a circular path. So how do you find this minimum velocity? Well, you got to focus at the highest point, because that's where the minimum velocity will be, and you do a free body diagram first. So what are the forces acting on the car as the car passes through the highest point? What are the forces acting on it? We have two of them. We got gravity down, mg is always down, and then there's also a normal force, which I know is weird for a lot of students to see normal force being drawn down because you're so used to seeing normal force up. But look, if you're looking at my calculator right here, I set my calculator on the table. Which way is the normal force on the calculator? Up, because which way is the table holding the calculator? Up. But if you have an object that's going through a loop on the underneath side, which way is the surface pushing on the car? Down. The track is holding the car down. It's pushing the car down. And why do we call normal force normal force? Normal means what? Perpendicular. So it's still perpendicular, right? It's perpendicular to the surface. All right, so we have mg down, normal force down. Now yesterday we talked about sign conventions for circular motion. Whenever you have a circular motion problem, make the center of the circle positive. You always, always, always want the center to be positive. Because why? When an object's in a circular path, what always points directly to the center? The acceleration and the net force. The net force and the acceleration. Because look, let me take my keys. Ready? I'm swinging my keys around my head like this. At any point, which way is the total force on the keys? Ready? Here. Which way is the total force on the keys? To the center. The keys are being pulled to the center. If the net force is to the center, the acceleration's to the center, right? And I also showed you yesterday a little vector exercise on how to show that your acceleration's to the center. Okay, so the acceleration's to the center, and that's the reason you want the center to be positive. Because look, you're going to go like this. You're going to sum the forces, blah, 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 blah. What does the sum of the forces equal? ma. Do you want this a to be plus or minus? Plus. Make the acceleration plus. The way you do that is by making the center of the circle positive. All right, so let's sum these forces for real. So looking at the car at the highest point, we have normal force to the center and mg to the center. So they're both positive. Normal force points to the center, mg points to the center. What is the sum of the forces always equal? ma. Now, this a is a special a. It's a centripetal. How do I know it's a centripetal? Because the car is in a circular path. Whenever an object is in a circular path, there's a centripetal acceleration. And we have an equation for centripetal acceleration. It's equal to v squared over r. Okay, so we plug that in. So what we have now is normal force plus mg equals mv squared over r. Now, what happens to the normal force as the car, so say we send the car through this loop 10 times, okay? We're going to send the car through the loop 10 times. Every time we send it through, we're going to send it slower and slower and slower. What will happen to this normal force as the velocity gets smaller? Does the track have to push harder, or does the track push softer? Softer. The normal force gets what? Smaller. Until finally the car goes through so slow that the normal force is equal to 0.0000000000000. Somebody tell me when to stop. Stop right there. Okay, good enough. So the normal force gets super duper teensy weensy. Very, very small. You guys know what I'm saying? So is it still touching the track? Barely, dude. Barely. So for all practical purposes, what can we do to the normal force? Just set it to 0. Just set the normal force to 0. What you're left with is this. What happens to the m's? The m's cancel, and you get v equals square root gr. That is how you find the minimum velocity at the highest point. Basically, the trick is the normal force goes to 0, and what you're left with is mg is the centripetal force. Does that make sense? Normal force goes to 0. The minimum velocity is square root gr. All right, now let's look at maximum velocity. So everybody got that copied? Yo.
Where did you get the A?
This right here? Okay, this is a given. Look, back when I was first teaching, I used to derive centripetal acceleration. Yo, the quiz? Give me like 2 minutes. I'm almost done. Or maybe like 3 or 4. Yeah, when I was first teaching, I used to derive this. The textbook derives this equation. It's the equation for centripetal acceleration. V squared over r. Just treat it as a given. All right, maximum velocity. So maximum velocity would be like this. So say you have a road, and then there's this bump in the road that happens to be from a perfect circle. Right? It's physics. Things like this only happen in physics, where things are perfect. So you got this bump in the road, and the bump happens to be perfectly circular. All right, so this car comes along, okay? If this car travels too fast, what's going to happen? It's going to fly off the road. It's going to leave the circle, right? So for a situation like this, there is a maximum velocity. It's basically the same thing we just did, but the problem that we just did a minute ago, where was the object? The object was under the track. Now it's on top, right? So we're looking here for the max velocity. What is the maximum velocity that this car could have and still stay on the road? So how do we do it? Start with a what? Freebody diagram. So at that point right there, we got mg down, and now normal force is up, right? The surface is holding the car up. Okay, center of the circle is positive. Always make, whenever you have an object in a circular path, see right here? We have a circular path, right? Make the center positive, because what points to the center? The acceleration. You want your A to be plus. Your acceleration points to the center. All right, so let's sum the forces. The center is positive, so we have mg minus the normal force, because the normal force points away from the center. Sum of the forces equals ma. What type of A is that? Centripetal. So we can plug it. That's a centripetal acceleration. So centripetal acceleration is v squared over r. Okay? Now, the normal force, again, if this car, so imagine we send the car 10 times over this bump. The first time it goes slow, right? The first time the car is like put, 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 real slow. Is there any danger that the car is going to fly off the road? No. So then we send the car over again faster and faster and faster and faster. As the speed of the car increases, what happens to the normal force? It gets smaller, right? Because the faster it goes, the less the road has to do. The road doesn't have to push as hard. Does that make sense? And then finally, it reaches a velocity where it leaves the road, right? So we'll set the normal force equal to 0.00000000000. Tell me when to stop. No, don't. Okay, more. 0.00000000001, right? So is the normal force technically still there? It's technically, I mean, the car is technically touching the road, but let's just, for all practical purposes, bye-bye normal force, right? Cross it out. What are you left with? You're left with mg equals mv squared over r. The m's cancel. Again, guess what you get? The same equation. So look, Vmax and Vmin, it's really the same thing. You know, I mean, it's the same equation. When do you have minimum velocity? Minimum velocity is if you're when? Underneath the loop, and then maximum is if you're on top. But it's square root GR. Yo.
On the midterm or any FRQ, do we have to derive that equation from summing forces, or just...
You could memorize it, but here, actually, I was going to say this. My recommendation to you is don't memorize. The fewer equations you have memorized, the easier it is on your brain. Like, look, I've been teaching physics now for I think this is my 17th year. If you saw me somewhere like a month from now, and you're like, Spaldo, what's the equation for minimum velocity inside a loop? You know what I tell you? I don't know. I got to figure it out. You know, I would not memorize this. What should you memorize? You should memorize oh yeah, the normal force goes to 0, right? So then the only force you're left with is mg. That equals ma. You know, you figure it out. You know, I wouldn't memorize square root gr. All right, man. That is the lecture. Tomorrow we'll do homework day.